our program, Understanding Climate Change by Dr. Ryan Shadbolt, PhD. This guest lecture spans introductory topics regarding climate change systems, science, and solutions. Questions from the audience are welcome and encouraged. Dr. Ryan Shadbolt is an advising specialist within the Department of Geography, Environment, and Spatial Sciences at Michigan State University. He has previously held faculty appointments at Central Michigan University, Saginaw Valley State University, and Northland College. Let me hand it over to Dr. Ryan Shadbolt.
Good afternoon. Thanks for having me today. My experience is in climate change and variability. Spent most of my life in Lower Michigan. As she mentioned, I've held appointments at CMU, Saginaw Valley State, and most recently at Northland College. Over the course of my career, I've published scientific literature in the area of climate variability and climate change. Though I feel like, for me personally, the biggest impact that I have had in my career has been working directly with students. And so that's why I decided to return back to Michigan State University last summer, now as an academic advisor and teaching specialist, where I teach a senior seminar and also a general education course titled People and Environment, where we focus on the interactions between people and climate change. The primary source for the material, the figures that I'll be showing you today, is from Andrew Dessler's textbook on modern climate change. This is the textbook that I'll be using in my People and Environment course starting in January. It's starting to look increasingly more so like we'll be online in the spring as well here at Michigan State University, although no formal announcement's been made yet. So I'd like to break this lecture into three parts. We're going to first look at the symptoms or the effects of climate change. And then secondly, today we'll look at the science and get into the causes of climate change. And then thirdly and lastly, I'll leave you with some suggestions about potential solutions on what we might do going forward. So to get us started here, I want to take a step back in geologic time. This is a relatively small window in comparison to Earth's entire history of a little bit more than 4.5 billion years. We are just looking at the Cenozoic era here in this figure. It starts about 65 million years ago there on the left-hand side, and the present day is on the far right. And this is looking at temperature over that 65 million years. And you may ask yourself, okay, how do we know the temperature over that time period, given that thermometers are a relatively new type of technology? In fact, we've only had thermometers for a few hundred years. That's correct that we don't have actual temperature measurements of geologic time, but we do have signs that nature provides us that allows us to estimate Earth's historic temperature. Primarily what we have to rely on, we're looking at millions of years like this, are oxygen isotopes, and we can gather that information from ice, soil, and rock. And we're looking at on the order of millions or billions of years. We're mostly focusing on sediment cores and rock layers. What we can very quickly see during this Cenozoic era is that temperatures were generally decreasing during that time. You may be familiar with the mass extinction of dinosaurs around 65 million years ago. The leading theory behind that is still an impact with Earth. That is theorized to have resulted in widespread wildfires and perhaps volcanic activity, both of which would have emitted a lot of carbon into the atmosphere. And that's what's responsible for the increasing temperatures there that reached a spike at about 55 million years ago. That PETM stands for the Paleocene Eocene thermal maximum. And then temperatures have been on a general decline since that time. And the gray bar on the right-hand side shows you the most recent roughly 400,000 years. You see temperature mostly on the decline. Yes, we are still in the depths of the most recent ice age that has persisted for about 55 million years. We're going to zero in on that gray bar, shows us the last 4 million years. We can see temperature decreasing generally over this 4 million years. We can also see the overall variability of temperature increasing during that time. Again, this is still going to be relying on geologic evidence and oxygen isotopes to estimate the temperature values. You see a lot of variability over this length of time. Most of what was controlling Earth's climate throughout this period would have been changes in solar output, changes in Earth's orientation with respect to the sun. Temperatures were mostly cooling over this 4 million years. In the last 1.5 to 2.5 million years is what we refer to as the Pleistocene epoch, which was kind of the last major advance of glaciers. This reached its most recent maximum about 18,000 years ago, which would still be at the very far right-hand side of this figure. We have a gray bar here again. This is now looking at just the last 400,000 years. So we're going to zero in on that. Temperature is the solid black line. And we can see that there's a kind of a repetitive cycle where temperature tends to warm up rapidly, and then it cools down a little bit more slowly, and then it warms up rapidly again. And that you can see we've had 5 spikes there over the last 400 or so thousand years. Present day is on the far right-hand side, and we are resting comfortably right now at the top of another one of these peaks. If the last 400,000 years tells us anything, you can use this in a predictive sense to imagine that Earth's temperature is probably due for another cooling over the next 100,000 years. The other variable we have on this figure is carbon dioxide, or CO2, which is an important greenhouse gas. And its atmospheric concentration, scale over here is on the right-hand side, historically has ranged between 180 and 280 parts per million. So if you were to take a sample of atmospheric air and divide it into 1 million parts, usually less than 300 of that million parts would be composed of carbon dioxide. It, by volume, makes up a very small portion of the atmosphere. But the fact that its volume does vary, as illustrated over this figure, that's what's important for us, because as it increases in its concentration, it means it absorbs more energy in the atmosphere, so we tend to have warmer temperatures when CO2 concentration is high. And you can see a very strong relationship between these two lines. The dashed line is carbon dioxide concentration in the atmosphere. When carbon dioxide concentration is high, temperature tends to be warm on Earth. So as we look at this last 400,000 years, temperatures tend to warm, and when that happens, ice tends to melt, so glaciers would retreat during those periods. And as temperatures have cooled, that's allowed glaciers to advance. And we went through a warming a little bit more than 100,000 years ago, then went through a cooling, and then this most recent warming is what we reside in currently, and that's now referred to as the Holocene epoch, and that's what you see on this figure. This is showing us the last 11,000 years. The gray shaded area kind of shows you a range of our confidence in these values as we have measured them from things like ice cores and geologic evidence, again relying primarily on those oxygen isotopes to estimate the temperature. The recent spike here at the end coincides to the last couple hundred years, and that very closely corresponds to the Industrial Revolution on a global scale. So now let's take a look at the actual temperature record. I want you to focus at the top part of the figure first. So this is looking at our thermometers that we use at our surface weather stations across Earth's surface. Most of them are located on land. We do have some located over the oceans. Our thermometers have existed for several hundred years, but in terms of having a worldwide network of weather stations takes us back to about 1880, end of the 19th century. And taking us through the present, this figure, we have removed the seasonal cycle, so we remove some of that noisiness within each year. The temperature values with the seasonal cycle removed are that's the thin gray line, and you can see a lot of interannual variability. And then we use a 5-year smooth average, that's the bold black line. It allows us to better see the overall trends. You can see that temperature decreased from about 1880 until about 1910. Global trends then increased from about 1910 to 1940. They kind of reached a plateau from 1940 to about 1970. And then we've been on an increasing trend again since the 1970s. Overall trend since 1880, you can see, has been on the increase. The warming has not been equally distributed, so this is part of why historically, us climate scientists, we would often refer to the term as global warming, and you've probably noticed that we've been increasingly moving away from that. The reason for that is that there's a misconception that when we say global warming is that people sometimes think that that means that all of Earth is warming at all times, which is not in fact the case. In any particular year, you can see that there have been cooler years at the bottom of each one of these lines, and there are warmer years. There's a lot of variability from year to year. There's variability from one location to another. There are examples on Earth that cool over time. But the majority of Earth has warmed in recent years. So I think it's safe to say that we have a warming climate overall, but the globe is not warming at all times at all places. To take a little bit more of a regional look at it by latitude, if we look at the higher latitudes of the northern hemisphere, that's the thin solid line down here, and you can see that region has experienced the greatest amount of warming in recent years. Locations closer to the equator, that's the dotted line, have experienced less warming, and locations in the southern hemisphere, that's kind of the dotted and dashed line at the bottom, that's experienced the least amount of warming. And the little figure inset down here kind of illustrates why, and it has to do with the land versus water contrast in the two hemispheres. We have a lot more land in the north, a lot more water in the south. Land tends to heat and cool more rapidly, so that has a lot to do with the warming trends. Also, the ice loss in the Arctic Circle has increased the rate of warming. We'll get to that a bit more in a later portion of the talk here today. Now, as I mentioned, most of the surface stations are on land, but we can take a close look at ocean temperatures. This is dating back to the late 1950s, and the overall trend, again, it has been increasing, especially since the 1970s, but you can see the magnitude of the temperature values. The scale here shows a much smaller temperature trend. Water has a much higher heat capacity, so it takes a longer time to heat up and cool down. But it is, without question, the ocean is warming just by small amounts. So we have warming temperature over ocean, warming temperature over land. Question is, what's this going to mean? And the biggest consequence is the disintegration of Earth's ice sheets. We can look at this in a variety of different ways. First, we're looking at mean glacier length. Units here are in meters, and we can look at this by, we've divided it into 5 different regions, and you can see that the trend is nearly the same for all 5 regions. The mean glacier length was consistent from 1700 through about 1850, and since about 1950 through the present, mean glacier length has decreased. We can also look at this by ice extent, or the area. So this is looking at ice by its 2 dimensions. We gathered this information from satellite imagery, so the record only takes us back to the 1970s, since that's when satellite imagery has been most commonly used. This is looking at just ice extent over the Arctic Circle. We can clearly see that that extent value, these are in units of millions of square kilometers, has been decreasing rapidly, especially in recent years. We can also look at this in terms of cumulative ice loss. So as the mass of ice is lost, we should see the value in this case increase, and we see it going up. This is dating back to 1992. So with the ice loss on Earth, as we're converting from ice to liquid, some of it's also converting to gas, but a lot of this is converting to liquid water. It's going to be finding its ways into the ocean basin. And so we should, as a consequence, see sea level increasing. And that's indeed what we've been measuring from both surface and satellite data collection. This is taking us from 1993 through the present. And depending on which exact years you look at on this figure, from 1993 to 2010, the annual rate of sea level increase was a little bit more than 3 millimeters per year. In more recent years, since 2010, it's been increasing more like 5 millimeters per year, which doesn't sound like a lot if we're talking about the units of millimeters, but this is the global average. There are definitely regional differences, some areas where it's increasing much more rapidly than others. Okay, so wraps up our first portion on symptoms or effects of climate change. We're concerned mostly about that ice disintegration. That's why I wanted to focus on that. I'll pause for a second here. If you do have questions, you can leave that in the Q&A chat box, and I'll see an alert as we go along, and so I can address those questions as we move through. But as long as I don't see any questions popping up there, I'll keep plugging along with the lecture here, okay? So the next part is on climate science. We know, if we're looking at when we learn a lot of these concepts in an introductory physics course at any university, we know that all objects are emitting energy. My body, my cell phone, the tabletop that my computer is sitting on, the wall here in the room that I'm working in, every single solid surface is emitting energy. And its temperature is going to tell us something about the type of energy that it's emitting. There is a relationship between wavelength of energy and its temperature. We can see the different types of energy here along the top. Sun's energy, for example, is mostly emitted in the visible range, all the colors of the rainbow that we can see. Cooler objects are going to emit on the right-hand side of this figure. So like the approximate temperature of a human body or Earth's surface tends to fall within the infrared wavelength range. So we often use infrared thermometers for measuring our body temperature or the temperature of Earth's surface. Figure here on the left-hand side is showing us the relationship between an object's temperature and the peak of its wavelength of emission. For the sun, its surface temperature is around 6,000 Kelvin. We're using the Kelvin scale here. It's very similar to Celsius. It just has the negative values of the Celsius scale removed. Sun's surface temperature is around 6,000 Kelvin. Its peak of wavelength emission is around 0.5 micrometers, which is right in the middle of the visible part of the spectrum. In comparison, Earth's surface temperature is cooler than 300 Kelvin, and its peak is around 10 micrometers, which is in the infrared portion of the spectrum. The other physics concept that is important is that the temperature of an object is directly, in fact, exponentially related to the amount of power that it emits. All these concepts allow us to use thermal imagery for measuring temperature of a human body, or in this case, a dog. A lot of us are relying on that technology right now as we measure our body temperature in the midst of this pandemic. We have our estimates of Earth-Sun geometry. So we know that both the Sun and the Earth are estimated as spheres. We know their approximate size. We know their approximate distance. We know the tilt of Earth's axis. We know the time it takes for Earth to make an orbit around the Sun, the time it takes for Earth to make one complete rotation over the length of its day. All of this information is necessary for us to determine the amount of energy that we receive from the sun. We want to know that quantity so that we can determine then what happens to that energy once it intercepts Earth's atmosphere. So that brings us to this figure. So you can imagine a ray of sunlight striking the top of the atmosphere, and the question scientists are trying to determine is what happens to that energy once it enters the atmosphere. Some of it's going to be absorbed, some of it's going to be reflected. On an average day, between reflection from the clouds, the atmosphere, and the ground, that is approximately 30%. That's just completely lost back to space. An additional 20% approximately is absorbed by clouds, dust, and the atmosphere. So it's absorbed before reaching the ground. And then the remainder, that would give us about 50% that's left, that ultimately does get absorbed by Earth's surface. And where that absorption happens, we get warming at the ground, and we can actually feel that with our hand or measure it with a thermometer. Now, in comparison to the sun, Earth is much, much cooler, so the energy that Earth will later re-emit, because it's a solid body like anything else, Earth is also emitting its own energy. So that brings us to this figure. The energy in this case is mostly infrared. And the important takeaway of this is that what we refer to as the greenhouse gases, so that's gases like water vapor, carbon dioxide, methane, nitrous oxide, those are the key ones right there. They are relatively transparent to incoming solar radiation, but they are effective absorbers of Earth's outgoing infrared radiation. That whole idea is what is known as the greenhouse effect. It's the absorption by gas molecules of Earth's outgoing energy. Because these gas molecules are located close to the ground, because they're affected by Earth's gravity, most of that absorption occurs close to the ground. And so we're in effect, as Earth emits energy, those greenhouse gases absorb that energy. It's warming the lower atmosphere, which indirectly then warms Earth's surface. That is the greenhouse effect. Greenhouse effect is generally a good thing because it keeps our planet at a comfortable temperature. The question we're trying to understand now is, have we reached a point where we've added too many greenhouse gas molecules into the atmosphere and we're experiencing perhaps too much warming? We can look at the concentration of some of these greenhouse gases. This is carbon dioxide. If we look at the top part first, that's carbon dioxide concentration in the atmosphere over the last 10,000 years. We can see the very rapid increase corresponding to the Industrial Revolution. Our current value here in 2020 is around 415 parts per million. It's off the top of this graph. If we zero in on just the last 250 years, from 1750 close to the present, you can see the increase there again. And we are off the top of the graph around 415. And if we look at our direct period of record from instrumentation dating back to the 1950s, that's what you see in panel C. The actual concentration in the atmosphere of carbon dioxide is this kind of sawtooth line that increases up to around 400 parts per million. You see an annual cycle there that's driven by photosynthesis in the northern hemisphere. Again, because we have a lot of land in the northern hemisphere, most of the vegetation exists in the northern hemisphere. So as plants tend to photosynthesize during late spring, summer, and early fall, we get more absorption of carbon dioxide. And so the warm months correspond to the lower values on the curve. And then during winter time, when plants are dormant in the northern hemisphere, carbon dioxide concentration in the atmosphere goes up. So you see an annual cycle there. The gray line on that same figure shows us the actual emissions of carbon dioxide into the atmosphere. So if none of the carbon dioxide had been removed from the atmosphere, the gray line is what we would actually measure. And you can see that the sawtooth line, which shows us the actual concentration, is roughly half, which tells us that about half of the carbon dioxide is ultimately removed from the atmosphere. And Part of it is the photosynthesis of vegetation, but the even bigger player is absorption of carbon dioxide from the oceans. Oceans are containing a very large quantity, and without the presence of that ocean absorption of carbon dioxide, we can see that the concentration would be nearly double of what it is today. Methane also contains carbon. Methane is CH4. It's emitted also through fossil fuel combustion, like carbon dioxide. Carbon dioxide's primary source that we're concerned about is from coal-fired power plants, whereas with methane, there's a number of sources. It is a byproduct from natural gas combustion and extraction. It's also emitted from various types of agriculture, livestock agriculture in particular, and also rice agriculture. So next I want to summarize the major climate change foreseens. Most of these are natural. Most of these have been ongoing for the entirety of Earth's history. The first is geologic. So this is going to include everything from asteroid impacts with Earth, volcanic activity, and continental drift that's in response to plate tectonics. So as Earth's land masses move slowly across Earth's surface, which they're constantly doing, that's ultimately going to change local climates. Volcanic activity over the short term creates cooling of Earth's surface as solid material blocks. The solid material that's erupted from the volcano can actually, literally block incoming sunlight, so it cools Earth's surface over the short term. But the carbon dioxide emitted by volcanoes warms Earth's surface over a long term. Solar variability. Solar output does vary over long periods of time. There is also an identified 11-year sunspot cycle that controls solar output and has some impact on Earth's temperature. The figure here is showing us solar brightness since around 1980, and you can see 3 complete cycles of that 11-year sunspot cycle. You can see that in recent years, the trend has actually been downward for solar brightness. Probably one of the most important key components in recent years, I say that in recent as in geologic time, so still in the order of thousands to millions of years, what's been the largest control of climate change has been the variations in Earth-Sun relationships. And part of that has to do with the shape of Earth's orbit, which is oval or elliptical in shape, but that does vary over a cycle of 100,000 years. We also have a cycle that we can measure that has to do with the tilt of Earth's axis and its varying tilt over a cycle of about 40,000 years. And these 2 cycles are working independently. They both impact the angle of the sunlight. We're talking about the tilt cycle, and it has to do with our distance from the sun, which impacts the amount of energy we receive when it comes to the orbital cycle. But these 2 cycles working in concert tell us an awful lot about those cycles that we've seen in the past about glacial advance and glacial retreat. We also have cycles that occur internally within Earth's land and ocean system, both atmospheric and oceanic cycles. These are largely going to be in response, or they're going to be responsible for Earth's climate variability from year to year. In some cases, it's from decade to decade. And in many cases, we don't necessarily think of that as climate change. It's more related to climate variability, which there is definitely a gray area between what we consider variability and climate change. There are some examples of where atmospheric and oceanic circulations where they have changed dramatically and that has resulted in climate change. An example is a theorized ocean current slowing roughly 12,000 years ago, which resulted in a decreasing temperature on Earth's surface around that time. We didn't have instrumentation available then, so we don't have conclusive evidence of it, but there is strong geologic evidence that has occurred in the past. So the first four bullets on here, geologic, solar, orbital, axial, atmospheric, oceanic, these are really all natural factors that have been controlling Earth's climate and variability on a shorter time scale throughout Earth's history. We now add human activity into the picture. Our leading contributions are greenhouse gas emissions and also our ability to impact land cover change through deforestation and wildfire, things like changing agriculture to suburbs or changing suburbs to urban areas. All these changes of the landscape affects the amount of energy that's either reflected or absorbed. Taking all these factors together, there's an additional wild card that we have to add to the picture, and these are referred to as feedbacks. And we're illustrating just one important example of a feedback. In a very basic conceptual way, what we mean by feedback is it's something where you have a very small initial change that then perpetuates and magnifies into a much larger change over time. An example that you can all picture in your mind is the example of a domino effect, where you line up all this, you stand up and line up all those dominoes, you flick over just the first one, so that's the small initial change, and then you can pull your hands away and the dominoes take over from there and they knock each other down if everything is lined up correctly. There, in an analogous way, there are some examples of this in Earth's system, and what I'm illustrating with this diagram is what's referred to as the Earth reflectivity feedback, where we might have a very small nudge of warming, maybe from greenhouse gas emissions. That's going to usually result in an amount of ice melt, maybe at the Arctic Circle. As that ice melts, it's going to uncover usually a darker surface underneath it, either darker land surface or a darker ocean surface, depending on whether the ice is over land or water. But in either case, that darker surface that has been uncovered is going to absorb more energy and reflect less than what the ice previously was doing. And with a lower reflectivity is going to mean more absorption at Earth's surface, which then amplifies further warming, which then amplifies further ice melt, which then amplifies further absorption and less reflectivity. You can see the process becomes self-perpetuating until something else intervenes. And this is part of what we understand is going on in the Arctic Circle already, and why we've seen the ice extent there decreasing so rapidly in recent decades. Okay, so pulling all that together, let's take a look at the top part of this figure first. The gray line is, again, Earth's surface temperature. This is 100 years from about 1900 to 2000. We can see the same trends we saw before: warming in the early 20th century, stagnant, perhaps even cooling temperatures from about 1940 to 1970, and the warming temperatures since. We have developed climate models since the middle part of the 20th century. We understand the natural cycles that I've summarized very briefly for you over the last few minutes. We input those equations of physics into these computer models, and then what we have done in the top figure there is we've ran or executed that computer model's calculations over the period of time, and we've done this intentionally to correspond with this historic record so that we could compare its results to the actual temperature observations we've collected in the past. It allows us to see the model's performance. So the top panel is showing us the climate models being executed with only the information from the natural cycles, those natural types of climate forcing. So things like solar output, volcanic activity, atmospheric and oceanic cycles, orbital and axial cycles. And we can see that the models did okay in the early half of the 20th century, but after about 1960, there was a clear divergence. Earth's actual temperature went up. The models, if anything, were suggesting that Earth's global temperature should have decreased after about 1960. Perhaps our current warm period in the Holocene epoch, naturally speaking, was coming to an end. We'll probably never know for sure, but we can see that the models tell us that natural types of climate change alone can't explain what's happened, at least in the last few decades. So the second attempt at the bottom panel is taking the same models and now adding in the information we understand regarding human contribution to climate change. So land cover change and also our contributions of greenhouse gases. We ran the models again, compare it to temperature, and you can see it is a much closer fit. And this tells us that with adding human contribution into the calculations, we can very closely recreate Earth's global temperatures using computer models. So it shows us that the models can perform well if they have the correct information. Tells us that we can probably have some confidence if we then run the models forward in time in a predictive sense. But we can also use this as the smoking gun that shows that yes, human contribution is contributing to climate change. We can say that unequivocally in the last several decades, dating back to at least probably the 1970s. We have nearly unanimous support of that within the climate science community. Okay, so next up, let's talk about some potential climate change solutions. And one of the things I want to talk about in this portion is how climate change information is often used. I mean, you can take the same data sometimes and use it for supporting whatever argument you want to make. And sometimes it's important when you look at data that's provided to you is to think about not just what is shared with you, but what is not shared. And the reason why I say that is because a climate change activist may intentionally show you only the data from 1970 through the present, because you've seen already from a few of the figures I've shared with you that the temperature, globally speaking, has increased since the 1970s. So if you zero in on just those years of data, you can see that very nice increasing trend. I prefer to show the whole picture of the entire temperature record going back to 1900 or so, because that way we can see what's happened in the years prior to 1970. A climate change skeptic could take the same set of data, and you can see we have 7 bold lines on here. These are all examples where they've literally cherry-picked a range of dates so that they could find some downward slanting trends to indicate cooling trends. And so someone might look at just these years, 2010 to 2013 or whatever that is, and they say, well, temperatures have been cooling over just that time period. My response to that is that cooling trends over just a few years is not enough to make a conclusion about climate change. That's looking more at climate variability between individual years. It's usually agreed upon in the climate change community that if we're going to use the term climate change, it has to be a trend that has persisted for at least 30 years. That is, once you're beyond a 30-year period, you're kind of outside of types of natural variability in Earth's atmosphere and ocean system that reoccur on decadal scales. More data, the longer period that you have, the better, because it allows you to see the more complete picture. If you're only shared a small amount of data from a specific station or a specific number of years, there's probably a reason. There's probably a reason why some of the information is withheld. There's 3 big rebuttals that we tend to see repeated again and again when it comes to climate change. Some of these can be from a science perspective, a religion perspective, or an economic perspective, and also often you see these in combination. And these are just a few examples of phrases that we often hear in the climate community. Someone may try to approach denial or skepticism of climate change by saying, well, it's all a natural cycle. Hopefully today you have seen that there certainly are natural cycles that have controlled Earth's climate throughout most of Earth's history. But we have learned today that evidence shows us that human activity has also contributed to climate change, and it's probably the leading factor in the climate change over the last several decades, at least. Second objection is kind of from a religious perspective, which is making the claim, maybe an example would say, okay, God's in control, it doesn't really matter what we do in terms of our personal activity. My rebuttal to that would be that most religions also make room for the idea of free will, that we are able to make our own decisions, and those decisions do have consequences, and that we have to live with those consequences. So I think it's important for us to understand how our decisions affect ourselves and other people and other species and the future. A third rebuttal is more economic based, which is making the claim that maybe converting over to a renewable energy society is going to have an expense, and that's more dollars than some people are willing and wanting to invest. The rebuttal that I have in response to that is that conventional sources of energy from the fossil fuels like coal, petroleum, and natural gas, those sources of energy are only cheap because we heavily subsidize them with tax dollars. If we did not subsidize them so heavily, they would also be more expensive. All it really takes is the desire to shift those subsidy dollars, those tax dollars, from the conventional sources of fuel to more renewable and sustainable sources of fuel, and that expense is going to go down. If we want to look at this in an economic sense, this figure collectively is showing us climate change impact from carbon dioxide emissions, and we can look at those carbon dioxide emissions using 4 terms that we've divided here. Human population are the little plus signs, and these are just relative values compared to the year 1970. It's global values. Earth's population has gone up. Makes sense that the more people there are, the more carbon dioxide emissions there are going to be. Population studies give us pretty good estimates of what the population is going to be like during the 21st century. We're likely going to plateau somewhere between 10 and 11 billion by the end of this century. There's very little that we can do to change that. Natural rates of increase from reproduction are decreasing globally, but we're still going to see population increase over the course of this century. There's very little that we can do to impact that value. The solid black line is gross domestic product per person, so this is kind of a reflection of income per person. It's going to be very closely related to human population, and if we want people to remain out of poverty, we're going to want to see those lines staying in close relationship. So there's probably going to be very little that we do to change the black solid line. You can see that they're both increasing with time, which suggests that carbon dioxide emissions are going to increase with time. Where we've had the greatest impact are the dotted and the dashed lines at the bottom, and these are both in regards to our technology choices and how efficiency of our energy consumption has improved over time. The dotted line is carbon intensity, and its units are carbon dioxide per joule. So for each joule of energy we consume, the question is how much carbon dioxide is emitted. So as we improve efficiency of our technology, we will emit less carbon dioxide per joule. So that's why we see the values decrease for that. And then the dashed line is energy intensity, and that's the amount of energy we receive for every dollar we spend. So again, this has to do with the efficiency of the technology that we have. We've seen the greatest success with those 2 values, and I would argue that that's where we should continue to focus our energy. pun, I guess, intended in that case. So as we continue to increase existing efficiency of existing technologies, and as we convert from older types of technologies to more renewable and sustainable types of energy, we'll continue to see those values decrease. So return back to the idea of the climate models. We can run them in a predictive sense going forward, but the catch here is that we don't yet know what the future will look like exactly. We don't know yet what types of energy we'll rely on. We don't know exactly what the human population will be. We can make some guesses. And so when we run the models forward in time, we create what are known as climate scenarios. And these are 4 examples of those. RCP stands for Representative Concentration Pathway. And then the numbers have to do with the amount of energy that's been added in watts per square meter within the atmosphere. The lower the number, like the RCP 2.6, that's a scenario that's assuming slower population growth and a more rapid conversion toward renewable sources of energy. So our carbon emissions will be less in result. This is a simulation running out to the year 2100. The higher the number, the RCP 8.5, we can kind of think of that as our business as usual scenario, where if we stay on our current trends of population growth and current trends of energy consumption, that's the trajectory we would find ourselves on. So this figure is showing the total emissions, but you know through photosynthesis and absorption of carbon dioxide by the oceans that the actual concentration in the atmosphere is going to be something less, about half. So this is showing us the concentration. If we were to stay on a business as usual approach, this is now taking us out to 2200. Carbon dioxide concentration would be around 1800 parts per million, more than 4 times the current amount if we were to stay on business as usual. The more aggressive approaches toward population and energy consumption puts us below 800 parts per million, which is still double of today's value. Probably realistically speaking, we'll find ourselves probably somewhere in this range between the RCP 4.5 and the RCP 6. How the carbon dioxide concentration relates to temperature takes us to this figure. This is taking us out to the end of this century, 2100. So again, the 4 scenarios, business as usual would take us to a temperature increase of about 4 degrees Celsius over the course of the century. The most aggressive approach would be about 1 degree Celsius. Again, probably somewhere we're going to be in the happy medium here, around 2 or so degrees Celsius warming over the century. That's the target that a lot of studies are focusing on, is trying to limit the warming to either 2 degrees Celsius or in some cases 1.5 degrees Celsius, which would put us down here. The reason for those 2 numbers is that those are estimated as being kind of the upper threshold of where we will experience a more mass extinction type event. I mean, we're already seeing extinctions underway, but to try to head off most of that, folks in the biology sectors of climate change are trying to focus on keeping warming somewhere between the range of 1.5 to 2 degrees Celsius over this century. Okay, so I shared a lot of information, but I think the takeaway that I always try to leave my audience with is always be eager to learn, read and listen to stories about climate change. Try to do your own research. Always question the information that you are provided or not provided. You know, try to figure things out on your own and ask questions when you don't understand. Be willing to communicate with your friends and family about climate change. See what they think about it. Share what you know. Find out what they know. You know, try to share information. And probably the most critical piece of power that we have as citizens is our ability to vote and help determine who our lawmakers will be. Climate change legislation can be enforced at the very local level, and certainly we can make our own personal decisions and lifestyle choices. Certainly, strategies can be made at the international level, but probably where the decisions will have the greatest impact is going to be both within our own federal governments and also within our state governments. So state and federal elections, I think will have the biggest impact over this century. So that wraps this up. I believe that the lecture today is being recorded and that will be shared, but I have recorded a previous version of this as well. I recorded it actually into 3 separate parts: symptom, science, and solutions. So those are some links provided for you there as well if you'd like to ever revisit this content another time. All right, with that, I'll be happy to address any questions the audience has. I thank you for your time today and for sticking it out with me over this last 50 minutes.
I don't see any questions so far, Dr. Ryan, and I'm also texting a chat. I mean, just giving them, if they have any questions, you're welcome to ask questions, and he's ready to answer your questions. I don't see it, and thank you very much, Dr. Ryan. It was a wonderful presentation. We really enjoyed it. I really appreciate for all your time. And it is actually a complex subject. And we heard that expert view based on research. You did a great job. And also you gave a good overview of the climate change, starting from prehistoric days. You also provided a great graphical representation of the history. And also you clearly explained in 3 different stages. That's really important. The science behind the climate change, and I gave a good understanding of climate change, how it impacts us. Really, it is scary when we go further. We don't know what is going to happen. And thank you very much. I really appreciate your time.
Yep, you're very welcome. My pleasure. Take care, everyone.
Thank you. Thank you all for attending this program, and stay safe.